Welcome to the lesson for section 3.2, derivatives of exponential functions. In today's lesson, we are going to try to learn what is the derivative rule for computing the derivative of an exponential function that is a function of the form a to the x, a number to a variable power. So this is different than the power rule because the power rule, remember, has the x in the base, number in the power. Okay, so different from that, we have number in the base, x in the power. So we are going to use the limit definition of the derivative to see if we can come up with a rule for this. So we're going to say, well, d dx of a to the x, applying the limit definition of the derivative. That is, remember, the limit as h goes to 0 of f of x plus h minus f of x all over h. That's just the definition. But then I'm going to use, instead of f of x, my function is a to the x. So this is going to be the limit as h approaches 0 of a to the x plus h minus a to the x all over h. Okay, so now I'm going to use a rule of exponents that we usually use in the reverse. Okay, so I'm going to rewrite a to the x plus h, okay, because that is a base, and I have added two exponents together. When do you add exponents together? When you're multiplying like bases. Okay, so I'm going to rewrite this as a product, a to the x times a to the h. So instead of a to the x plus a to the h, we have a to the x times a to the h minus a to the x all over h. And then I can factor out an a to the x from each term. So I pull out the a to the x, and I'm left with a to the h minus 1 all over h. And a to the x, this factor here, a to the x, there's no h's in that. So this is not affected by taking the limit as h goes to 0. So I can take this a to the h and treat it like a constant because there's no h in there that's changing. So I can pull that out of the limit. So this is going to become a to the x times the limit as h goes to 0 of a to the h minus 1 over h. And we don't know this limit. We could try to calculate it numerically, but it is some constant. It just comes out to a number. And we could write this as a to the x times some constant. Okay. And here's the amazing fact. That constant turns out to be the ln of a. Okay, so we haven't studied computation of limits in depth enough to show that that's true, but this turns out to be the ln of a. So there is our derivative rule for a to the x. A to the x times the ln of a. So let's do an example. I want to calculate d dx of 3 to the x, evaluate the result at x equals 0. So I'm just going to apply the rule I just learned that says that d to the x of a to the x is a to the x times the ln of a. And I'm going to apply that where in the case where a is 3. So this is going to be 3 to the x times the ln of 3. And then I'm going to evaluate that when x equals 0. So we write that as d dx of 3 to the x evaluated when x equals 0. That means plug a 0 into the formula here. So you get 3 to the 0 times the ln of 3. And 3 to the 0 is 1, so it's just the ln of 3. So to interpret that graphically, that is the slope of the tangent line to y equals 3 to the x at x equals 0. And here's a picture of what we just found. This is the graph of y equals 3 to the x. And this line is the tangent line to the graph at x equals 0. So here's x equals 0. It's tangent at that point. And you can see that it has a slope of the ln of 3. We can just try to verify that numerically. So if I look at the slope of this line, it's like this. Okay, so change in y over change in x, we would say, oh, I don't know, it looks like the change in y is a little bit bigger than 1. It's like 1 and this tiny little bit here. So we would say, I don't know, maybe 1.1. I'll use approximately here, 1.1 over 1, um, which is about 1.1. And the ln of 3, if you put that in your calculator, it's 1.098. So it does check out that the slope of this line is ln of 3. This is your first activity for lesson 3.2. You can pause the video at this point and try the activity. When you're done, watch the video for the solutions. Okay, we are going to compute the derivatives of 7 to the x, 2 to the x, and e to the x, and evaluate them all at x equals 0. So if we let f of x equal 7 to the x, that means that f prime of x, its derivative, would be 7 to the x times the ln of 7, which means f prime of 0 would be the ln of 7. Okay, and then we're going to repeat this for 2 to the x and e to the x. So if f of x is 2 to the x, the derivative would be 2 to the x times the ln of 2. And that means that f prime of 0 is just the ln of 2. And then finally, e to the x, f of x equals e to the x. So f prime of x would be e to the x times the ln of e, but the ln of e is just 1. So f prime of x is just e to the x. And so f prime of 0 is 1. Remember that the derivative evaluated at 0 is the slope of the tangent line at x equals 0. So on the next slide, we're going to look at the graphs of 7 to the x, 2 to the x, and e to the x, and look at the slopes of the tangent lines. So this first graph is y equals 7 to the x. And you can see that the tangent line we drew at x equals 0 is pretty steep. It has a slope of ln of 7, which is approximately equal to 1.95. Pretty steep slope. And we do know that exponentials with a larger base grow faster than exponentials with a smaller base. So this graph is y equals 2 to the x. And the slope of the tangent line at x equals 0 is the ln of 2, which is approximately 0.7. So you can see less steep than this one. And then e to the x, this is the graph of y equals e to the x. And remember, e to the x is about 2.718. So the slope of this line was 1. And just reminder, e is about 2.718. So that is somewhere between 2 and 7, closer to 2 than it is to 7. So the slope of the tangent line at 0 should be between 0.7 and 1.95. And it is, it's 1. Okay, chapter 3 is all about learning derivative rules and shortcuts. And so we're just going to list the ones that we've learned so far. So we learned the power rule in our previous lecture. And it said that the derivative of x to the n is nx to the n minus 1. And today we learned that the derivative rule for an exponential, a to the x, is a to the x times the ln of a. And we have a special case of this rule for e to the x, d dx of e to the x. If I just apply the a to the x rule, I would get e to the x times the ln of e. but the ln of e is 1. So e to the x times 1 is just e to the x. So we usually think of this as a special case of this rule. And we say the derivative of e to the x is e to the x. And then we have two more general rules where if we are taking the derivative of a sum or a difference, you can take the derivative of each term separately and then add or subtract them. So this would be f prime plus or minus g prime. And then the derivative of a constant times a function, you can do c times the derivative of the function, or c times f prime, same thing. We have reached the second activity for section 3.2. Go ahead and pause the video at this point, work through the problems in this activity, and then come back and watch the video for the solutions. Okay, number one, we're going to write down the power rule and the formula for the derivative of an exponential, a to the x. So we know that f prime of x, if f of x is x to the n, f prime of x is n x to the n minus 1. And g prime, if g is a to the x, then g prime is a to the x times the ln of a. Okay, compute the derivative of each function below. So f of x is e to the x plus 5 to the x. So I'm going to apply the exponential rule to each term and just add the two together. So f prime of x is going to be, the derivative of e to the x is e to the x. And you can write times the ln of e if you want, or you can just remember that the derivative of e to the x is e to the x. Okay. The derivative of 5 to the x is 5 to the x times the ln of 5. Ln of e is just 1, so this is e to the x plus 5 to the x times the ln of 5. Okay, if g of x is 2 to the x plus 3, we want to find the derivative. And our derivative rule for an exponential only applies to functions that look like a to the x, not a to the x plus something, okay? So I'm going to have to do a little bit of work on this function before I can apply the exponential rule. So I'm going to use that same rule that we used in the definition of the derivative earlier in the lesson, where I have a base and I have two exponents being added together. I have an addition in the exponent. And when are exponents added together? When you multiply like bases. So I'm going to rewrite this as 2 to the x times 2 cubed, which is 8 times 2 to the x. Remember, we cannot write that as 16 to the x. Okay, because the order of operations say you have to do the exponent first before you do the multiplication. So you can't do the 8 times 2 before the multiplication. Okay, I mean before the exponent. All right, so we just have 8 times 2 to the x. There's our function. And to find the derivative, I'm going to use the rule that says when you have a constant, it just sort of comes along for the ride. Okay, it's going to be 8 times the derivative of 2 to the x. So that's going to be 8 times 2 to the x times the ln of 2. F of t equals 3 to the t times t squared plus 5t to the first plus t to the 1/2. Okay, so I added the to the 1 power so that I could use the power rule on that. And let's see, this is an exponential, power rule, power rule, power rule. Okay, so you can tell the difference because when the t is in the exponent, that's the exponential rule. When the t is the base, that's the power rule. So I'm just going to apply the derivative rules term by term. So f prime of t, the derivative of 3 to the t is 3 to the t times the ln of 3. The derivative of t squared, remember the power rule says bring down the power, copy the t, reduce the exponent by 1. And then for the derivative of 5t to the first, we bring the 1 down and multiply by the 5. You get 5. Copy the t, reduce the exponent by 1, and we get 0. And then the power rule on the last term, I'm going to bring the 1/2 down, copy the t, reduce the exponent by 1. 1/2 minus 1 is negative a half. And now I'll just do some simplification. So I have 3 to the t times the ln of 3 plus 2t plus 5, because t to the 0, that's just 1, plus 1/2 t to the negative 1/2. R of s equals pi to the s plus s to the pi. So this one is really trying to stretch your math muscles in terms of reminding you, which one am I using, the power rule or the exponential rule? You have to remember that s is the variable. S is the variable. So in the first case, it appears in the exponent, making this an exponential. And in the second term, the S appears in the base, making this a power. So I'm just going to make a little note like exponential power. Okay, because S is the variable. Pi is just a number. So R prime of S is going to be, this is an exponential. So the derivative would be pi to the S times the ln of pi. And then when I do the power rule on s to the pi, we bring the exponent down in front, we copy the s, we reduce the exponent by 1. So pi minus 1, I'm just going to write pi minus 1 instead of getting a decimal approximation. And that is all done. P to the x equals e to the negative x. Okay, so again, we have a formula to take the derivative of an exponential function, but it has to look like a to the x. It can't look like a to some stuff with x's in it. To apply the rule, it has to just be a to the x. So I'm going to have to change this function a little bit to make it look like a number to the x. So I am going to use the raising a power to a power rule in the reverse direction that you're probably used to seeing it. Okay, so I'm going to rewrite this as something to the plain old x. Okay, because if I want to use the a to the x formula, I have to have this written as a number to the x. Okay, so instead of e to the negative x, I could write it as e to the negative 1 to the x. Because when you raise a power to a power, you multiply the exponents, and negative 1 times x would be the negative x. Okay, so now I'm just going to rewrite this. I've got p of x is e to the negative 1 to the x, and e to the negative 1, oops, I wrote that wrong. Should be negative 1. That is playing the role of a. Okay, so now I can apply my exponential derivative rule. So it's going to be a to the x times the ln of a. So a is going to be e to the negative 1 to the x times the ln of a, which is e to the negative 1. And then I could simplify this. So this is going to be e to the negative x, and the ln of e to the negative 1 is negative 1, because logarithms and exponentials undo each other. So the ln of e to anything is the thing. So this is times negative 1, which simplifies to negative e to the negative x. Um, Another way to think about simplifying the ln of e to the negative 1, it's just a little aside here. Some people might remember the rule of exponentials that lets you, um, I'm sorry, the rule of logarithms that lets you take, if you take the ln of something to a power, you could bring that power down in front and you'd get negative 1 times the ln of e, but the ln of e is just 1, so this is negative 1 times 1, which is negative 1. Okay, h of x equals e to the negative x times e to the 2x plus x e to the x plus 7. So I do not have a good rule for taking the derivative of a product. Remember, we talked about that in our previous lesson. So what I'm going to do instead is multiply these two things together before I try to take a derivative. So I'm going to do the distribution before I take derivatives. So this is going to come out to e to the negative x times e to the 2x. I'm multiplying like faces. I'm going to add the exponents, and I get e to the 1x. Okay, and then e to the negative x times x e to the x. So multiplying like bases, e to the negative x times e to the x. When you add the exponents, you get 0. So this becomes x e to the 0. And then when I do e to the negative x times 7, that's pretty straightforward, 7e to the negative x. So to simplify this, I get e to the x plus x, because anything to 0 is 1, and plus 7e to the negative x. And now I can apply my derivative rules um, pretty straightforwardly, okay? So the derivative of e to the x is e to the x. The derivative of x is 1. And the derivative of 7e to the negative x. Well, the 7 is just a constant in front of a function. So I'm going to keep that there. And then I'm going to say we're going to take the derivative of the function e to the negative x. And this problem we actually just solved in the previous example. And it came out to negative e to the negative x. So this final derivative is going to be e to the x plus 1 minus 7e to the negative x.